How to design an electronic amplifier that can implement a wide range of gain from attenuation to, let's say, a sizable gain using just one op-amp and one potentiometer is discussed in this video. In this implementation, we are realizing an attenuation minus 25 dB to a gain of plus 55 dB, a substantial dynamic range, let's say about 80 dB of gain range, just using one operational amplifier and one variable resistor. So aside from the op-amp, we have one adjustable variable resistor that can be analog potentiometer or digital potentiometer or RDAC. For this one, the value P of the potentiometer is nominal 10 kilo ohm, depends on design, can be adjusted. The Viper of the potentiometer is connected to ground, and the alpha on one side of potentiometer is basically means that the resistor this side is between the Viper and this node is value alpha times P. So alpha is just a scaling. Of course, the other side will have a between the Viper head and this node of potentiometer, that side has a value of 1 minus alpha times P naturally. So alpha, of course, is a scalar that is between 1 and 0, depending on where the Viper is positioned. If you're doing analog potentiometer, this is a mechanical Viper, so that we have to mechanically adjust it. If we are using, let's say, digital potentiometer, the position of this Viper can be electronically adjusted, so it depends on application. Now, for the op-amp, it's important that what type of op-amp we select. So Vn is a DC or AC, let's say, input signal. The bandwidth of this signal, which is basically defined by the application, whether it's an audio or whether it's a video application, is actually going to enforce the type of op-amp you're selecting. For example, at the end of this video, I'll talk about a bunch of options from, say, Texas Instrument or analog devices, which provide different choices for, let's say, gain, bandwidth product of the op-amp. But that would basically be enforced by the type of application you select. Now, with that said, bear in mind that there are two main resistors in this example implementation. One is R1 at the input 4.7 kilo ohm nominal, the other one R2 in the feedback loop of the operational amplifier 47 kilo ohm. The small resistor R47 ohm is just a stabilizer to make sure that the circuit is just remaining stable in a reasonable range, but the value can be adjusted depending on what example or what implementation you have. In real implementation, depending on the type of op-amp, there might be a need for a stabilizing cap between the negative terminal and output. The value of this cap is nominally 10 picofarad up to 100 picofarad, let's say, depending on application. I'm not going to have it here because it's just a stabilizing cap to make sure that the circuit is fully stable for the whole bandwidth of operation. Now, let's talk about the implementation, the analysis, basically. So let's make sure that the two supply voltages in dual supply design plus minus 10 volt are there. So basically, op-amp is biased. And let's observe that the output of op-amp is connected to negative input terminal as shown. So it means negative feedback is there for the op-amp. Therefore, op-amp is operating in linear region. And hence, the virtual short is valid for the op-amp, which means we can assume that the voltage at positive input terminal and negative to input terminal is the same, enforced by, let's say, the negative feedback that we have. Okay, so how's the circuit working? So what do we have is, let's say we have a transfer function from Vn to this node, which means to the positive terminal, and then from positive terminal we have a transfer from positive terminal we are to negative terminal enforced, so whatever voltage we find is the same here, and then from there we have a transfer function to the output. Effectively, we just have a sort of a non-inverting amplifier. So let's take a look what is the minimum maximum gain for that. Depending on the position of Viper, we have a voltage division between R1 and the series of R and alpha 1 minus alpha P that is connecting R to ground. So effectively, this is in series with R, obviously, as we can see. So let's, and then we get to ground. So the circuit looks like this. So here is the op-amp. Here is the positive terminal, negative terminal. Positive terminal, you can see on one side via R1 we are connecting to Vin. So let's show it. Via R1 we are connected to Vin. And on the other side, let's say here, positive terminal, on the other side via R and 1 minus alpha P goes to ground through the viper of the potentiometer. So we have this connection, R plus 1 minus alpha times P. From negative input terminal of OpAmp, we have a connection to via the R2 feedback resistor to the output. So we have this connection, R2 to the output of the OpAmp. And then via negative terminal and series of R and then alpha P, so alpha P in series with R, we have connection to ground via the viper of the potentiometer. So we have one effective resistor with a value R plus alpha times P and grounded. So this is the well-known non-inverting amplifier. So non-inverting amplifier topology. And the gain of that is clear. So of course, again, the same voltage is appearing here. We have two resistors R2 and this one effectively in series. We have these two resistors effectively in series. So from Vn to this node is just the voltage division. And then from V to V out is another voltage scaling or division. I can say, in summary, I can say the AV or overall voltage gain, which is V out over Vn, can be divided into V out over V, so V out over V, and then V over Vn, so V over Vn. And we can observe now how the circuit is functioning. So before I just show you quick, the computation of gain formula is not difficult, but before that, let's intuitively examine for this AV or overall voltage gain of the circuit. Of course, it has a minimum and it has a maximum value. And we are trying to establish a link between this minimum and minus 25 dB and this maximum and 55 dB. So I'm going to show that we are realizing that minimum minus 25 dB and maximum plus 55 dB in this circuit. What is the situation for minimum? If we move the head of the viper of the potentiometer to this beginning node of, let's say, or terminal of the potentiometer here, that would mean alpha is 1, given that alpha is in this side. So here is alpha equal to 1. Well, that means that the only resistor then is the small resistor R. So effectively with alpha equal to 1, let me show you with different color. So with alpha equal to 1, this becomes 0. And therefore, just we have R. This whole thing is 0. And the voltage division here becomes R. So V over Vn becomes R over R plus R1. Okay, so we get basically a heavy attenuation from, say, this portion. So let me put it this way. When alpha equal to 1, we get maximum attenuation from this guy, which means in this scenario, R over R plus R1, which is 47 ohm divided by 47 ohm plus 4007 ohm, which means 1 over 101. So we are attenuating the input signal by 1/100th roughly to get to this node. And then at the same time, the gain component, this component, is minimized as well, because what is that gain? Look at what we get. From V to V out, there is just a scaling of voltage because these two resistors are series. So we get V out over V is simply, let me move this resistor so that we have enough space here. There you go. Okay, so we have simply R2, 1 plus R2 over R plus alpha P. That's the scaling factor, of course, for a voltage division that we have between these two resistors to get from V to V out. So as you can see, with alpha set equal to 1 in denominator, we have, so if alpha is set to 1, we have the largest denominator. That means we have the smallest gain. So in summary, all I'm trying to say is, let's say this is equation 2. So from equation 2, when alpha equal to 1, we have minimum, let's say, value for V out over V, which in this case turn out to be, if we compute it, given that alpha is 1 and P is 10, so we get V out over V equal to, we have, let's say, 1 plus R2 is 47 kilo ohm, 47,000 divided by 47 ohm, plus alpha is 1 times potentiometer is 10K. Let's neglect 47 ohm with respect to, or compared with the 10K. So effectively, this translates to, so roughly on the order of, let's say, 5.7, because this is 4.7 and we get plus 1, which is 5.7. So that's the minimum gain we get, lowest gain for V out over V. So now we can say what is AV total, because we found these two components of the voltage gain for the scenario where the Viper is at this position, which means alpha is 1. So in that case, we get AV, let me write it here. So we get AV equal to roughly, so now roughly equal to 5.7, that's the first portion, times 1 over 101. So if we compute this, it turns out to be roughly 0.056. And if we take a 20 log out of AV, which is the way we compute the dB version of the gain, we get to 25 dB negative. So that is minus 25 dB. That's the attenuation we get from this circuit. This value is clearly roughly 1 over, say, 18 or on that ballpark for the attenuation of the voltage scale, minus 25 dB. Okay, so what about the highest gain? So we found the, let's say, the lowest gain on this side. That's minus 25 dB. Let me write it here. So I'm going to say here, turn out to be minus 25 dB. For the maximum side, what is the maximum gain in this circuit? Okay, so that would be exactly the other way. If I move the Viper from this position all the way to now, so let me just do it this way, all the way to now here, which means alpha is 0 now. What happens? Well, we actually minimize the attenuation, basically maximize the amount of transfer of V into V, because what we are doing is now we are by setting alpha equal to, say, 1, alpha equal to 0, which is the case when we are here, so the head of Viper is at this terminal. Basically now R 47 ohm is the only resistor observed between negative terminal and ground. So what happens is this resistor is maximized by alpha 0. So we get R plus P, and R is 47 ohm. P is 10 kilo ohm. So it's roughly 10 kilo ohm that we have here. And we have 4.7 K here. So what happens is this time, this portion is maximized. Okay, so I'm going to write it here. When alpha equal to 0, we get, let's say, maximum value, or let's say minimum, we get V over V in maximized. Okay, so we get V over Vn equal to, so the transfer of V in to V here at the positive terminal and negative terminal as well, equal to roughly, as I said, we have 10 kilo ohm approximately, and then we have 4.7 kilo ohm, and there is a voltage division between them. So 10 kilo ohm plus 4.7 kilo ohm. So effectively, we have 10 over 14.7 approximately. So that is the V over Vn, this portion. What about the gain portion of the circuit? Well, that's maximized. You can see that. So here in the gain portion that is following formula number 2, the alpha is now 0. So the denominator is minimized, which means the whole thing is maximized. So the gain with alpha 0 now is R2 over R plus 1. So we can say, in this case, the V out over V is maximized as well. And is V out over V is now 1 plus the feedback resistor 47 kilo ohm divided by very small 47 ohm. So we are talking about 1 plus 47,000 divided by 47, which means the gain is 1001 for the second, so for the second component of the gain, which is this guy. So this one is 1001. Therefore, the overall gain is equal to, so the overall gain is equal to V out over V times V over Vn, which in this case is 1001 times this guy, which is 10 over 14.7. Okay, if you compute this, it turns out to be roughly 682, which is on the order, if you again compute the 20 log 10 base 10 of AV, it turns out to be on the order of 56 dB. So we actually obtained better than what was mentioned, 55 dB. The circuit actually provide up to 56 dB of gain. All right, so I just showed that what's happening with respect to overall gain and attenuation of this circuit with single potentiometer and single op-amp. And this is a very practical circuit, can be used. Let's say if you're interested in audio application, maybe you can go with sub $1 op-amps. Analog Device has many choices. There are, for your information, there are on the order of more than 5,000 op-amps available from the likes of DigiKey or Mauser with the gain bandwidth on the order of, let's say, greater than or equal 50 megahertz. Why do I mention that? Because with a gain close to 682, or let's say roughly 1000, if the gain bandwidth is 50 megahertz, then in order to support this gain, the circuit effectively can do up to, say, 70 kilohertz of bandwidth if it is 50 megahertz op-amp. So that means we can, Vn can be up to 70 kilohertz, let's say, for this Vin at the input of circuit. Definitely good enough for audio applications, for high-end audio applications. If you want video applications, say up to a megahertz bandwidth for the input signal, then we need a scale of 20x. So up to 20x, not necessarily 20x, say 15. So in that case, then instead of 50 megahertz, let's say op-amps. So these two from Texas Instruments, let's say OPA 607, or let's say from Analog Devices that are 88091, these are 50 megahertz roughly gain bandwidth op-amps. So, but if you want to go to video application and even higher, then let's say OPA 817, 800 megahertz op-amp from FET input actually op-amp, which means a very low offset and input current. From Texas Instrument could be a very good choice. Of course, it's a little bit more expensive on the order of, say, it starts on the order of, I believe, let's say $3 to as high as, if you go to extreme scenarios of say 8 to 10 gigahertz gain bandwidth product, which is very interesting. That is OPA 855 from Texas Instrument. This one is close to $8 to $10 per op amp. So at this time, so of course these value will change. But what I'm trying to say is, for the normal audio application, there are 5,000 op amp to select, potentially up to 5,000 op amp with 50 megahertz of gain bandwidth. As you get to more demanding, let's say video application, maybe we better go to gain bandwidth of more than 500 megahertz. And even upward of gigahertz, then we are talking about options available on the order of, say, a couple of hundred op amp, and maybe about 100 op amp. Definitely you have options that can be purchased from Mouser or DigiKey. So it's important, the goal here is to mention that depending on the application, it's important that proper op-amp is selected in terms of gain bandwidth so that we can support the maximum frequency range of input. I hope that this coverage of the choice of op-amp and also the analysis of the circuit is helpful in terms of how this circuit is practically implemented. Thanks for watching.